So this is the second part of this problem. So towards the end of the first part, we were looking at this example. So let's just go over it again. So we start from 7 and we can at most reach this 7. And then this 7 would actually take us all the way to the end, so we will only need to jump 1 step and 2 steps. So my current algorithm is incrementing the minimum number of jumps every time it crosses the current farthest, which we have explained is incorrect. So instead of incrementing min jumps every time we cross the previous farthest, we should be incrementing minimum jumps when we have gone over all of these elements, and then we have now found the next farthest we can go, meaning that, so first jump, we can jump all the way here, and then everything here in between, they could be jumping somewhere closer than this, then it wouldn't matter, or it could be jumping from this 9 will definitely be crossing over, and this 9, this 6, even this 6 will cross over to that. So what we want is to find out the farthest any of these elements can go. So all of these 7 elements from the first jump, what's the farthest any of these can go? Let's say that the farthest any of these can go is here, even though right now it can jump all the way to the end, but let's just say it only can jump to here. Then we would have done 1 jump and then 2 jump. So with those 2 jumps, that's the farthest we can go with those 2 jumps. So we're always trying to see what's the farthest we can go with the minimum amount of jumps. And once the farthest we can go crosses the last element or reaches the last element, that's when we have the final result. I think that's if you think about it this way, let's say, so first jump we can go here, so we need only 1 jump to come here, and that's the minimum number of jumps to get here, because if you take any other way, it will be more than that 1 jump. So the minimum amount of jumps to get to all of these is just 1 jump. Then let's imagine that we don't have these high numbers here. Let's say the highest we can go from any of these is just here. What that would mean is after the first jump, minimum amount of jumps we need to get to this point would be that first jump plus another jump from any of these, the farthest we can go. Since it takes one jump to jump to any of these, then we calculate the maximum we can jump from each of those, and then if the farthest we can go is that means we'll take one jump to whatever element and then another jump to from that element to that. Right. So this would be the farthest it can go with 2 jumps, and this is also for this index the minimum amount of jumps is 2. Okay. I think that's the right logic. So let's try to code that. So we still want to calculate the farthest we can jump for each index position. So the algorithm we need is something like this. So when we are here, we store the farthest we can jump. And we need to store that somehow, because we need to mark this, because we need to go over every single element between that and this, including this one, and we need to calculate the farthest it can jump for all of them, and then store the farthest it can go. And once we reach this, that is when we update, okay, the farthest we can go is here, and that is when we update this min jump. That's only when we increment, not before, only when we have gone over everything. That's when we increment. Okay. We still need min jumps. We need farthest. We need one variable to store this index before we finish all of this. Okay, let's call it last position. So for this, let's just start over. So if okay, so I mean, we want to do this. There's got to be some kind of while loop that's doing this while the index hasn't reached the last position. What if we do, well, no, let's just try. Well, or no, okay, so for all of these elements, if farthest is I plus nums I as usual, so that's the farthest it can go. And then next round we have farthest that. So we'll keep doing this and calculating the farthest until we reach if I equals last position. So when we do reach this, what will we do? Farthest. So this is calculating the farthest it can go. When I is here, that's when we want to update the last position to be the current farthest it can go and increment min jumps. Okay, and the next one next time the farthest will be because I'm thinking, so we had okay, wait, so it's 0, last position is 7. So when we are here, we only incremented once, but next time we actually need to implement another increment min jump one more time. So I guess we could do this, but I don't think that's the best way. Not even sure if that's correct. What if we start from 0? If we start from 0, then the first round we will calculate the farthest to be 7, and I is not equal to, okay, I is equal to 0, so last position is now 7. Okay, that might work. Oh no, 1 and 1. So what's happening here? We have 0, 1 jump, and then we have 3, farthest is not at the end. Well, I mean, could it be something like this? Oh my god, okay. 107 or 109, that is good. Oh, I see. Yep. So this apparently works for most cases except for these special cases. We have 0. I mean, I really don't want to write something for a special condition there. That will not be the clean solution. But I'm curious to see the other test case that's not passed though. So let me just do that for now so I can see if so this is totally cheating. If length is 1 and 0, then we return 0. Oh. Okay. Okay, I'm glad this works. So we have only one element. If farthest is bigger. Okay, is there anything we can do to remove that and also remove this +1? So each time we first calculate the farthest it can go. If that is reaching the end, we want to return, but we're actually taking a step. So there's some kind of ordering we can adjust so it makes more sense. So what if we, okay, first we see how far it can go. If I is equal to last position, then we update that to be the current farthest it can go, and we increment 1. Could we do this instead? equals last position. I equals last position. Or what if we do if I equals last position? So that's when we want to update the last position. Min jump plus 1. Or if it's already reached the end, then we can increment. I don't think this is the right solution. Oh, I see. It does work. But it does not solve that problem. So that was read 0, further set 0. That is still gonna return 1. Okay, well, I cannot think of how to remove that right now. And this also looks very redundant. Okay, let's just check out some other solutions. Let's do time and space analysis first. Oh my god. Time. What are we doing in here? We are traversing the input list once, doing calculations along the way. So it will be linear time, which is the optimal. And space, we are using constant space. So linear time, constant space, as good as it gets. Alright, now let's look at some other solutions. Okay, let's see. Answer and farthest for I in range. Oh wait, why am I doing range for that? Okay. Oh wait. Range. Okay, now I'm actually unsure. Python range, isn't that the end is exclusive? Not included. Yeah, right. So that's should be a problem there. If I see. If this is answer plus 1. Wait. If I is equal to end. So that's what it's doing here, but it's also doing. Oh, yeah, I see. This was like what I was doing before. I was just doing that +1. It's just doing +1 and then break. So this solution is basically so it was this. This was what I was doing before. Farthest, return that +1, so that it has the same effect that if it's equal, then yeah, so that will be the same. But again, it wouldn't work if we only, yeah, it does not work if I remove that. Okay, let's look at the top solution. Jumps, current, furthest, okay. If that's equal, then we increment end. So this solution doesn't have this part. And the rest of it is the same. Well, let's try that. I'm not sure if that would work. Yeah, that does not work. Drop 0, 0, 0. Well, it does go to 1 less than what I'm going to furthest. The rest of it is really the same though. So this actually doesn't pass. So I'm not sure if their solution will pass the current problem. What if how about we just try this? Let's just try this. This is Java, so let's just try their solution. It's using nums instead of a. I would really be surprised if this works though. Oh wait. How is it possible that this works? And it's beating 99% of users. That's crazy. How come this works in Java but not in Python. What am I missing here? Okay, so there's one difference. Okay, let's try that again. Oh wait, what? Wait. So this totally works, but when I was doing all the way until the last element, it did not work. Why is that? Okay, let me see. Why do we want to go all the way until the second last instead of the last one? So what is happening at the second last element? When we are here. Here. Min jump. If I is equal to last position. Then we increment one more. So what is this loop doing? So for here we have the farthest to be 2, and then for this we have the farthest to be 4. And now when we're here, that's when I is equal to the last position. Okay, so now the last position will be updated to 4 and min jump increment again, so we have min jump 2. And what happens then? We are here. We're here. It's not equal to last position, so nothing happens. And then what happens at the last element? We are standing there and it is equal to the last position. Last position. The farthest. Okay, so it doesn't really explain why we want to iterate until the second to the last element. Okay, so no one is writing about that. So, okay, so why is it that we don't need to check the last element? I mean, I know that we don't need to check it because then we've already reached the end. And we are assuming that we can always reach the end. Okay. So this for loop is just calculating the farthest we can go from each position, and then every time we have reached the point where we have not gone over everything before that, that's when we update from last time. Last time we can at most reach this current I, but now we have a new farthest, so we're gonna update that. So which means last time with how many steps there are, we are able to reach this index, and then now with just one extra step we can reach this index. Because why is it just one extra step? It's because we have not calculated all the possible max distance from taking that one extra step all the way until this index. So we know that with one extra jump we are able to reach this new farthest. And that's why we are incrementing this way. And we don't even care about returning when it reaches the end. Why is that? This is not a good example. So we are here. So when we are standing here, we already reached the end, but we don't even need to return right away, and we can just keep going because the last position. So this was the last position after we jumped the first two, and then we are going over this and this before we update this part. So with this, farthest will be 4, and nothing happens. And then we are here. We go into this condition. We update that position to be the farthest, which is the last one, and we increment our jump. So when we were standing here, we had one jump, and now we increment another jump. So we have 2 jumps, but we are not done with our for loop. So we are still going. So now the last position is actually 4, and we're gonna go to index 3. Farthest is 4 again, but last position is 4, so we're not there yet. Okay, understand now. Okay, so the last step, when we are here, we are already here, so we don't need another jump. So why is it that we can continue to do this even though we've already found, like, it's already it should already be over? We don't need to actually go through this after we calculate this 3. Why is it that we can still go over that? It wouldn't affect the result. So let's my god, it's already 40 minutes again. Okay, this is the last part and then we're done. So let's imagine that there's another element 1 after these 5 elements. So first jump we can at most reach this one, and with 2 jumps we can at most reach this 4. So with 2 jumps our last position will be this 4, and we haven't reached the end yet, so we still need to continue here and here and here. And since I is always gonna go to the second to the last element, it will continue to go. Okay, so last position is at 4 and our I is not at 4, which means we will update the new farthest, which be 4 plus 4, 8, and we'll increment our jump. So since I is gonna go from 0 to the second last, it will continue to go until, basically it will continue to go until the last position is that last element or over that, because if last position is not the last element or over, then it's something before that, then this I will actually increment past that and continue to do another jump. So if we had a bunch of elements left here, this I will always go over the last position until it reaches the second last one, and it will stop there. So that explains why this for loop will be correct even though we don't jump out. And why it would continue to increment mean jumps all the way until the second last element. Okay, alright, that's it. I'm not gonna say more about this, and it's already 10:30 p.m. and I have early morning meeting at 7. So I will do another problem tomorrow. That's it. Good night. Bye.